A very good day to you, sir. My name is Losini, matrix number 98336. I am coming from Group 6. Today, my group mates and I will be presenting our group project. My group is consist of 5 members, which is me, Batmaa, Eunice, Ruth, Odilon, Puteri, Liyana, and Macximillian and Ruth. We implemented and evaluated the round-robin scheduling algorithm using Python, leveraging its capabilities to extract data from an Excel sheet and compute performance matrices. By analyzing various time quantum values ranging from 5 to 60, we measured key metrics such as turnaround time, waiting time, and number of interruptions. This comprehensive evaluation highlights the impact of time quantum selection on the algorithm's efficiency and functionality. Now, I'll be talking about the code output. As I said earlier, the time quantum used are 5 to 60, and the results are average waiting time, average turnaround time, and number of interrupts. Average turnaround time shows how long it takes for a job to be completed after it is submitted. Average waiting time indicates how long job waits in queue before being executed. Number of interrupts refers to the number of context switches happening during job executes. As you can see here, for these 3 time quantum, which is 5, 10, 15, these are the results for average waiting time, turnaround time, and number of interrupts. For the time quantums for 20, 25, and 30, the average waiting time and the average turnaround time are the same, except for the number of interrupts. For 20 is 977, and time quantum 25 is 774, and time quantum 30 is 644. For the time quantum of 35, 40, and 45, the average waiting time and average turnaround time are the same as the previous slide, and number of interrupts are different, which for 35 is 549, time quantum of 40 is 480, and time quantum of 45 is 420. For the time quantum of 50, 55, and 60, the average waiting time and average turnaround time are exactly the same. For average waiting time and average turnaround time, it stabilizes around time quantum of 25, indicating diminishing returns from increasing the quantum beyond this point. For number of interrupts, it decreases as time quantum increases, with fewer interrupts happening at larger quantum. For example, 339 interrupts at quantum 5 versus 318 interrupts at quantum 60.
Greetings everyone, my name is Puteri Imanina Abdullah and my matric card number is 100804. I explain the code for the round-robin scheduling setup. This code assigns a time quantum to each job and tracks their execution and interruption. Current_time tracks elapsed time. Ready_queue stores waiting jobs in the cyclic order. Completed_jobs records finished tasks, and waiting_time start at 0 for all jobs. Burst_times maps jobs to the total CPU time, while interrupts_counts calculate how often jobs are preempted. These setups ensure efficient scheduling and manage context switches effectively. We start with a while loop that runs until all jobs are completed. Within this loop, newly arrived jobs are added to the ready queue. The algorithm checks if a job has arrived by comparing its arrival time with the current time and ensure the job isn't already in the queue or completed. If the ready queue is empty, the current time increments and the loops continue. Next, the algorithm picks the next job from the ready queue and processes its current instruction. It checks whether the current instruction index is within the job's total instruction. If so, it retrieves the instruction type and cycle required. If the instruction is CPU, the algorithm processes it with a time quantum, calculating the time slice as the minimum of the time quantum or remaining cycles. The current time is then updated by this time slice. The loop continues until all jobs are processed, ensuring efficient scheduling and processing of tasks. Now let's look at calculating and printing job metrics. This code sorts job by the number and calculates waiting time, turnaround time, interrupt counts, and completion time for each jobs. It then prints these metrics. It also calculates the average turnaround time, average waiting time, and total interrupts across all jobs, providing insights into overall job scheduling efficiency.
Hello, my name is Odilon, Corino, Anak, Junit, and I'm going to explain the comparison and evaluation of the performance of different time quantum. As you can see here, this is the chart of average turnaround time against time quantum. ATT rises slightly from 5 to 20 and stabilizes at 19,730.73. Equilibrium is reached beyond a time quantum of 20. Smaller quanta increases context switches and overhead, but larger quanta reduce overhead but show no gains after 20. A time quantum of 20 optimally balances efficiency and responsiveness. Next, This is the chart of average waiting time against time quantum. Waiting time initially rises, then stabilizes with increasing time quantum. It increases from 18,867.07 to 19,071.80 as quantum grows from 5 to 20. Smaller quanta causes higher waiting times due to frequent context switches. Stabilization occurs at 19,071.80 when quantum reaches 25. Larger quanta minimize context switching, improving CPU efficiency.
Hi, my name is Macximillian and my matrix number is 101815. So from the chart and result of the calculation regarding the number of interrupt experienced when applying the round-robin scheduling algorithm, the round-robin scheduling algorithm evaluation shows that a low time quantum of 5 results in a high number of interrupt 3939, causing significant context switching, overhead, and inefficiency. Increasing the time quantum reduce interrupt such as 1964 at quantum 10 and 318 at quantum 60 by allowing longer CPU time slice and fewer preemption. However, there is an optimal time quantum range that balances low interrupt with reasonable waiting and turnaround times. While longer time quantum reduce interrupt, they may increase the waiting time for such processes. Understanding the relationship between time quantum and interrupt is crucial for optimizing schedule algorithm, enhancing resource management, and improving overall system performance.
Hello, my name is Eunice, Ruth, and today I'll be presenting the recommended time quantums and the conclusion. So based on our analysis of various time quantums values ranging from 5 to 60 units, we recommend a time quantums of 20 to 25 units. When looking at the performance metrics, for time quantum equals 20, we observe about 90.7 thousand average turnaround time and 977 interrupts. For time quantum equals to 25, we also see that there's 19.7 thousand average turnaround time but with less interrupts at 774. The middle range provides a good balance because it minimizes turnaround time without excessive context switching. The waiting times are more reasonable compared to smaller quanta. And lastly, the number of interrupts significantly decreases from smaller values but doesn't improve as dramatically with larger values. However, it is important to note that there's no one-size-fits-all solution. The optimal time quantum depends on the specific job list and the system requirement. The most suitable time quantum minimizes the average turnaround time, average waiting time, and the number of interrupts. Different systems have different needs, such as systems with frequent user interaction benefit from smaller time quantums for better responsiveness, whereas systems with less interaction performs better with larger time quantums to reduce overhead. Ultimately, the ideal time quantum is context dependent, varying according to workload characteristics, system design, and performance goals. Thank you.